Alright, welcome to the video of reactions of ethylene. So we have seen previously that ethylene is an important molecule industrially because it makes a lot of commercially significant molecules. And so we're going to look at some of those reactions in this video. So let's write down why ethylene is so important. Okay, so it's used. Alright, so it's used as a feedstock to make commercially important industrial molecules. Now, why does ethylene do this? Right? Why does it react like that? And here's the chemical reason. Why? It has a reactive double bond. So why is a carbon-carbon double bond more reactive than a carbon-carbon single bond? Well, I'm glad you asked because I'm about to tell you. And this looks in a little bit of chemistry that we haven't looked at, and we're not really need to, but I want to explain to you why it's more reactive. Alright, so if we draw two carbons here, and we know that there's 4 valence electrons, and we have learnt previously that carbon wants to have a complete octet, so let's move those 2 valence electrons there, and then we form a double bond between the two. That is what we've looked at previously. Now, in chemistry there are different theories or models to explain observations. And there's different bonding models. And here is what they think is going on to explain why the carbon-carbon double bond is so reactive. So let's just rub this out for a second here. And let's draw it in, carbon, carbon. Now when two carbons bond, they rearrange, the orientation of the electrons rearrange into specific regions of space. And we've come across this idea before when we talked about the valence shell electron pair repulsion theory, which we used to talk about the shape of molecules. So in previous videos we said that when molecules have regions of electron density, those electrons occupy space in certain regions to create a shape of the molecule. Well, here a similar sort of thing happens when they bond. And so what happens is we have 2 electrons there, and those 2 electrons will bond. Now, I'm going to draw it like this. They overlap. Right? So they share and they overlap this region here, and that's called a sigma bond. You don't really need to remember the names, but I'm just telling you because it's part of the process of understanding what's going on here. So we have a bond there. Remember that there is a second set of electrons that need to bond to create this double bond, right? Now, electrons exist in different shapes. One is in, I guess you can consider it as the x-axis around an atom. Then there's also a y-axis. And so we have some electrons here which occupy another region. And so if these ones occupy this space here, above the carbon atom, okay, then you can have the 2 other electrons that are bonding, okay, and they can occupy other regions, right? So, but let's not worry about those at the moment, right? These 2 here occupy these top Y regions. So we have the other 2 here which bond onto hydrogen. I'll just draw them in, right? But these 2 here overlap in a weird way, and it's called a pi bond, right? So they sort of share this top region here, right? And that's called a pi bond. It's a little bit further away from the carbons. Because it's a little bit further away, it's more reactive. It's not held as closely together as these 2 here. And so when we talk about carbon-carbon double bonds being reactive, it's because these electrons exist in this upper y-axis area a little bit further away from the carbons than these 2 here. And so these electrons are more unstable and therefore more reactive. Okay? So that's the reason why carbon-carbon double bonds are more reactive. You don't need to understand, you will not be asked to explain why it's more reactive in terms of this, what I just told you. But understanding that sort of now you sort of go, okay, I understand now why a carbon-carbon double bond is more reactive than a carbon single bond. It's got to do with how the electrons are shared. All right. So all you have to say is that the carbon-carbon double bond is more reactive, and therefore it is used as a feedstock to make other molecules. Okay. All right, and that's it for that bit. So let's now delve in and look at the different things that are made. All right, so let's go across here now and see what's made. And I guess we could say there's some examples of what it's used for. And the first thing we're going to be talking about here is going to be looking at making ethanol. Okay. The second thing we're going to be talking about is what's called the bromine water test, or the bromine test. Right? I'm going to find a bit more about that, and we're going to do an experiment with that as well. And then C is making monomers. Okay, so ethylene is used as a feedstock to make ethanol, to make monomers, and to do this test here called the bromine test, which helps distinguish between alkanes and alkenes. And the reason why it does all that is because of the fact that it has a reactive double bond. Okay, all right, make sure you get that down, and we're going to check out ethanol and how we make it. Okay, the first one, making ethanol. Now, when we make ethanol from ethylene, it's called a hydration reaction. Okay, and so what we're going to be looking at here is we're going to be adding water to a carbon-carbon double bond. Because we're adding water, it's called a hydration reaction, right? You need to hydrate, drink some water. So we're going to be doing some hydrating here, and in terms of making ethanol. Now, what actually happens is it's an equilibrium reaction. Okay, an equilibrium reaction. And we're going to delve into that and really understand this, but this is what's going on. All right, so we've got ethylene here. And we do the equilibrium arrow sign, so that's how we draw it. This top one here means it can go from the left to the right, and this one means it can go from the right to the left. So we're going to be making water here, and what happens is this water adds to the double bond breaks, and we make an alcohol. Okay. Now, to do that, we need a catalyst to start the reaction. And so what we do is we add dilute acid. So I've put that on the top arrow to say to go from this way to that way. We only need dilute acid because we've got a reactive double bond here. So we don't need a very strong acid. We only need a small amount of acid. That starts the process happening, and the water adds to the double bond to give us our alcohol, our ethanol, right? We can go backwards. We can go backwards this way, and we're going to be looking at this backwards reaction in more detail later. But if we're removing water, so if we're starting here now and we're removing water, we would call that a dehydration reaction. But because we're going backwards, we need the opposite, and so we need to add concentrated, or conc, H+. Right? And you get a lot of questions in the HSC that say, what do you need to go from this to that? And you'll have to go, do I need dilute? Do I need concentrated? And you'll go, okay, weak double bond, doesn't need much energy, I use dilute acid. And if we're going from the OH back this way, you go, okay, well that's weak, so that must be strong. And if it's strong, I need a strong acid to break it. All right, so this is the equilibrium reaction that goes forwards and backwards. Okay, now why is this important? Well, let's have a look. Why is this process important? Okay, the first thing is we want to make ethanol industrially because it's an important solvent in medications. So in medications, so no longer do you have to swallow big tablets. If you're a young child and you try and give a young child a big tablet, they're not going to like it. You're going to be fighting them. So what we do is we can use ethanol as a solvent to dissolve a lot of the compounds in medicine, and that enables you to have liquid form and therefore ease of taking medication for children and also for the elderly. Okay, so I guess we could write here medications are in liquid form. The reason why it's such a good solvent, and we'll get onto this in more detail later, but it can dissolve both polar and non-polar materials. So if you think over here, right, if you look over here, we've got ethanol. This portion of the molecule is non-polar, right? You've got only dispersion forces there, so it's going to dissolve non-polar compounds. And this here is the polar region, because it's got the H there, H bonding. So ethanol is a very good solvent. It's sometimes called the universal solvent because it will dissolve non-polar and polar chemicals, right? All right, so that's important for medication in terms of its solvent abilities. We can also say that, once again, due to its solvent abilities, here we're going to be looking at things such as cosmetics. So disinfectants used in hospitals, medical procedures, operations to prevent germs, transmission and all that sort of stuff. So fashion industry, cosmetics, massive industry needing a solvent as for ethanol. Perfumes can also use them as well. So we can see here the importance of using ethanol is great for a lot of different reasons, and so therefore we need to make it. We make it from the hydration of ethylene. So it's really important that we practice and get this information down, do the quizzes, do your flashcards so you know this, it recalls off the top of your head. The next key, once you've got all this down, of course, is then how to answer questions. And this is why this part here is so important, to link and elaborate your responses. So when a question says, why is ethanol an important commercial molecule? Then you'll have to go into all of this. Okay, it's a solvent, it can dissolve both polar and non-polar, therefore it can be used as medications. And you link it, elaborate. If it's used in medications, liquid form. Well, what's the advantage of that? Well, ease of use for children and elderly. Therefore, greater dissemination of medication across society, etc., etc., etc. You want to link and elaborate and bring it back to the chemistry, okay? But you need to get all this down. You need to understand it, make flashcards, constantly do the quizzes that we have on Schoology, right? And get that recall really, really high so we can work on doing the answers. So that's hydration. Let's move on to the bromine water test. We're ready to examine the bromine test. Okay, we've seen that ethylene can react with itself as a monomer to produce polyethylene. Another type of reaction is the bromine test, and this one you're going to be looking in detail when we do the practical investigation in how we determine the difference between alkanes and alkenes. But just briefly, let us go through it. So the bromine test is when bromine is added, so it's an addition reaction, to an alkene. And this happens very, very fast, right? So on the side here, I'll just put up a picture that you can see bromine water in a test tube. It's brown. But when you mix that with an alkene, the bromine adds to the double bond, and therefore the solution goes clear. Okay? So if we think about it, we have something like this. Ethylene, we add the bromine adds to the double bond, and you'll learn more details on that in the future video, but it creates, which is a halo alkene. Reminds me of a song. Halo alkene. Halo because it's a halogen, and halo alkane. Halo because it's a halogen and an alkane. So this is called 1,2-di-bromo, and then we've got 2 there, ethane. So 1,2-dibromoethane. And because the bromine is no longer in the water, it's added to our organic compound here, we get a colourless solution. That happens only for alkenes in the dark. For alkanes, it doesn't happen in the dark, and so it remains brown. So it's a quick little test that you can use to distinguish between alkanes and alkenes, and we're going to look at that process in more detail in our prac episode. So that's the second reaction. Let's move on to how ethylene reacts with compounds to make monomers to form polymers that are industrially important. You use plastics quite a lot. Okay, you've got plastic bags, you've got plastics in shoes and chairs, in bins, electrical cords that you use for headphones, etc. So plastics are around, and they're polymers. And polymers are actually made up of single units called monomers. And so ethylene is is important starting material or feedstock to make those monomers. And the monomers we're going to be looking at is ethylene itself. That will then go to make polyethylene, right? So plastic bags, Glad wrap, etc. It goes to make another monomer called vinyl chloride, and that goes to make PVC. So we're going to look at these. And then we also make another one called styrene, which goes to make polystyrene. So let's check these out. The first one, of course, is the ethylene. The ethylene to polyethylene. Okay, so we're talking about monomers. So let's define what a monomer is. A monomer is a chemical that can combine with itself multiple times to form a long chain called a polymer. And in this instance, the monomer is ethylene, and so it contains a double bond. And we're going to look in a later video that this type of monomer, when it joins with itself, is called an addition monomer, and it forms a polymer. So here we have ethylene, another molecule of ethylene. Now what happens is that these two combine multiple times to make a polymer. This is how you draw it. So you put a little bracket around there, and you go in with the first carbon, put your two hydrogens in, then we go the next carbon, two hydrogens, next carbon, two hydrogens, and then the next carbon, two hydrogens, and we close our bracket. Now the ends represent any number of units, because these can be thousands, millions of units long. And so we're just saying this is the fundamental process where you get two monomers joining to make a polymer. Okay, so let's look about the names, because the naming is very important. You have to be able to draw the monomer, be able to name it, and then know what polymer it forms. So when we go to name it, there's two different ways we do it. There's the IUPAC name, or otherwise known as the systematic name. The IUPAC stands for the International Union of Pure and Applied Chemists. It's an organization that's responsible for creating the systematic naming rules for compounds. They also are responsible for naming the periodic table, the elements on the periodic table. So if you would discover an element, you've got to put it through to this organization and they will approve the name or not. So it's the systematic name, and for ethylene, it's called ethene. Okay, ethene. We've covered that before. The common name, and you could also say it's the industrial name, is ethylene. So draw a flashcard of ethylene, the IUPAC name and the common name, and you should be able to, within like a second, 2 seconds, recall this information. Now the thing is, it forms a polymer called polyethylene. There's two main types of polyethylene, which we're going to look in more detail in a later episode, but that's the first one, polyethylene. Let's now check out PVC. PVC pipes, PVC piping around your house, guttering, are made of PVC, along as of other things. We have PVC wraps that you can use. So what is the monomer that is made? Vinyl chloride. So let me draw vinyl chloride for you. It looks like ethylene to begin with, but then we put a chemical group, chlorine atom, right there. So we're going from ethylene to this compound here. It's not a simple one-step reaction. It requires 2 to 3 reactions depending upon the industrial process. You're not expected to know that, but you are expected to know that this monomer here is produced from ethylene, and from this monomer we make PVC. So when you get questions that talk about the important commercial industrial chemicals that are made from petroleum, straight away you should go petroleum makes ethylene, the ethylene makes vinyl chloride, that vinyl chloride makes PVC, which is very important to our society. Okay, that's the sort of thinking that you need to be able to do. All right, so let's have a look at how this happens in terms of when it joins. We're going to do this very basically because we're going to do it in more detail later. But we've got two monomers here. the same thing happens, that these double bonds break, right? So it's a type of polymerization known as addition polymerization, and we'll learn that that's characterized by the breaking of a double bond. So let's draw it. So we've got our carbon with two hydrogens joined to another carbon, hydrogen up the top, chlorine down the bottom. Then we have another carbon, two hydrogens, and then we have the next carbon, hydrogen, chlorine. So it's very important that you learn how to do that and that you can systematically work your way through, because you're going to get questions where they will show you two monomers you have no idea and you're expected to draw the polymer. Or you have the polymer and you have to work out what the monomer is. And it's just a matter of going, okay, one carbon at a time, I need to go back and double check the arrangement and make sure it works. Okay, so here we have the PVC polymer. Let's look at the naming of the monomer. The IUPAC name, that is the systematic name, is chloroethene. The common name is vinyl chloride. So that's for PVC, right? Once again, flashcard, memorize it, put names on them, be able to recall it, draw it on whiteboards, etc. Know what polymer it is made from, etc. So let's move on to the third one, polystyrene. Alright, the last one we're going to look at in this episode is polystyrene. It's made from a monomer called styrene. And once again, it looks like ethylene because it's derived from ethylene. Through a series of reactions, we end up putting a group on here that looks like that. Now let me just talk to you a little bit about that so you understand. Remember when we looked at fractional distillation, and we said fractional distillation was separating the hydrocarbons in petroleum according to their boiling points. We said that we had straight change versions, so we had ethene, propene, butene, pentane, octane, etc. We had alkenes and we had alkynes. We had branched structures, right? So we had ones like this with branching. But we also had cyclo compounds. So if I was to draw something like this, that's an example of a cyclohexane. Right? Well, I said hex because it's got 6 carbons, right? So I can have cyclopentane, etc. But this is cyclohexane. We can also have alkenes. So I can draw a double bond in there, and now I have cyclohexene. But we also have other ones as well called aromatics. So if I do this, we now have a situation where there's multiple double bonds. But not only that, aromatics are characterized by this following phenomenon. Notice that I've just drawn the structure again, but the bonds are in a different location, because with aromatics, these bonds are constantly moving. In reality, they're not really moving. It's not really a double bond. It's a hybrid. It's a cross between a single and a double, and the electrons are constantly moving around. And we call this resonance. It's a resonance structure. To resonate means to go backwards and forwards or change positions in a periodic manner, right, when something's resonating. And so this is what's happening here. The electrons are constantly moving, and so you can see I've drawn it here with a little circle. Sometimes that's drawn like that to say that electrons are constantly moving around. And this compound here is carcinogenic, so we aren't allowed to use it in high school level, but they are present in petroleum, and hence we're not allowed to have petroleum either at high school, because it is a carcinogenic substance. It's a hazardous substance because of the benzene rings. So we put a benzene ring there and we form the monomer called styrene. So if we add another styrene monomer like this, we're going to make those two join together to make the polymer. And it's the same process. So I want you to pause now, see if you can have a go at drawing it, and then press play again and see if you got it right. Okay, I'm going to draw it. We'll check you in a second. Press pause. Go on and try it. All right, how did you go? Okay, carbon, 2 hydrogens, carbon, 2 hydrogens, carbon, hydrogen at the top. Then we have our benzene ring, carbon, 2 hydrogens, carbon, hydrogen plus a benzene ring. That benzene ring can go up there as well. It just forms a different type of styrene, polystyrene I should say. So this here is the generalized reaction. Now let's look at the naming here. So IUPAC name, and this is a weird one. Okay, you've got to memorize this one because it gets a lot of students. It's called ethanol benzene. It's not ethyl benzene, right? It's not ethyl benzene, right? It's ethanol benzene. There was a question in previous years that got you to try and identify the correct one, and a lot of students picked ethyl benzene. It's ethanol benzene, and the common name for the monomer is styrene. Okay, so that's it. We've covered those monomers. Make sure you got the information down. You got all your notes down. Any questions, we'll iron them all out in class. You should be able to draw them, name them, have flashcards, etc. And I'll see you in the next episode where we look at bromine test in more detail because we're going to do a crack on it. Okay, very important reaction. See you soon.